Hey everybody, Bill Sky, the Assembly Guy, and we're going to do a special video today, and this is really came from a subscriber of mine, and I thought it was a really good idea to go over it. It's called memory alignment. What is it all about? Now, if you've never heard of memory alignment before, this is where you need to be. We're going to talk about it. We're not going to go into some of the technical details that you might see on like an Intel lecture on alignment, but we're going to definitely show you what it's all about, what good it is, and how your programs can benefit from it. So let's get going. Okay, memory alignment. What is it all about? There exists in assembly language the ability to align memory on a certain word size boundary. So you can align it on a byte, you can align it on a word, which is 2 bytes, on a double word, which is 4 bytes, on a quad word, which is 8 bytes. And this alignment of data is primarily for the sake of performance. Think of the CPU as having a certain sized pipe that allows a certain amount of water to come in. If you do not align that pipe just right with another pipe that's sending water your way, it's not going to be able to get there all at one shot. It's going to have to grab it from here and then grab it over there. I saw another description of this, like you have the CPU has a drawer that allows a certain amount of data in it, and if your data isn't aligned with the same dimensions of that door, you've got to grab part of the data first and then grab the second part in a second, what they call memory fetch. So it's definitely, there's a lot of analogies out there, but it's primarily for performance, so you don't have to do multiple fetches. However, in some circumstances, it is required by certain instructions in assembly language to actually have your data aligned, and we're going to see one of those. It also differs across different CPUs. Architectures, alignment is more important for RISC-reduced instruction set computing CPUs like the ARM or the MIPS than it is for CISC, which is complex instruction set computing, which would be like an Intel Pentium or x86-64. So as an example, there's a statement called FX save, which what it does is it backs up your CPU's floating point unit, the FPU. It backs it all up to memory. And why would you want to do that? Well, let's say you're writing a function that is going to do floating point arithmetic, which I haven't done a video on yet, but it's coming very soon. You haven't done that floating point arithmetic, but you don't want to mess up the floating point unit from the function that's calling your function. So what you do is you back up the floating point unit before you do anything within your function, and then you go ahead and do what you need to do, and then you restore it with the FX, I believe it's restore statement. The FPU, the contents of the FPU with this FX save statement is placed into memory starting at a label that you specified in the data section. We're going to see an example of this. And if the memory identified by the label is not aligned on a 16-byte address boundary, then the program really just dies. And here's an example of that code. So if you can see up above in the section.data, I have a 1-byte variable or label called test1, and right underneath that I say align 16. Then I create a variable or a label, very bad name here, called memory, and I say define byte with a value of 0 512 times, because the FX save statement requires 512 bytes to store everything in the floating point unit. And when I do the FX save down on line 23, and I specify the dereferenced memory variable or memory location called memory, it does it just fine. And as you can see on the left side, the program ran and ended. Same with the FX restore, RSTOR. That restores the FPU, floating point unit. So the program ran just fine. Let's take away that align 16. All I did was delete it from the code, and look at what happened. We got a segmentation fault. Nothing else changed in the program. I just took away the align 16, which we're going to talk about that statement in just a moment. So I didn't align it. And now I actually believe if I didn't have that test1 define byte 1H on line 7, if I didn't have that there, it may have worked because the assembler may automatically align each section on a 16-byte boundary. I don't know that for sure, but it sure sounds familiar to me. So But to be absolutely sure, it's a good idea to have that align 16 whenever you've got a statement or the memory must be aligned just correctly. So again, it's obvious to me that and in fact, it's even in the, and by the way, I named the FX restore statement incorrectly. It's actually FXRSTOR and not FX restore. So pardon me on that. So it's not just obvious to me, but it's actually documented in the programmer's guide, the Intel programmer's guide, that it must be aligned. The memory location where you're backing up the FPU must be aligned on a certain byte count boundary. So this is an example of an assembly language instruction requiring a certain memory alignment. So what actually is memory alignment? Again, memory is based on a power of 2 structure. This means that any data stored in memory should always load into a register from an address based on this power of 2. Now that doesn't mean that you have to do that. It just means that it's much more efficient to do that, because instead of doing multiple fetches of memory, let's say if you're moving data from a memory location to a register, instead of the CPU having to fetch data from the chips twice, it'll only fetch it once if it's aligned correctly. And you can also look at this, I've heard this talked about as an even memory address as opposed to an odd memory address. But that's not really 100% correct, because if you have an alignment on a 2-byte boundary, which is even, a 4-byte boundary, which is even, a 6-byte boundary, a 6-byte boundary is not really a power of 2, is it? So it's more of a power of 2 structure that you should do it. And in fact, we might even see some code today showing you that error. And the other thing that you need to think about is memory you need to think about it as if it's composed of blocks. Each block of memory has a size which can easily be read into the CPU with a single memory fetch. Not your move, okay, not your add from memory, but actually below that in the machine code where the code is actually, the CPU is actually going out and fetching the data from the memory chip. These blocks, for instance, might be of size 4, size 8, 16, 32, 64. It depends upon the data address bus coming out of and into the CPU. And it definitely is determined by the architecture of the CPU. So if a CPU operates with 4-byte blocks, then memory is structured in the same way. Now, I don't know of any CPUs today that are based on a 4-byte block. Normally they're 32 or 64 these days. And in fact, we're even going to see an example where Intel talks about its most current CPUs as being aligned on a 64-byte boundary. So if you can place a number into the CPU starting on a 4-byte block address, and you can store that entire number within the 4 bytes, then that data is considered to be aligned. In other words, think about that water pipe. If you can stick all of the water, if the pipe that you've got is the same size as your data, or your data, I should say, is the same size as the pipe, then the data just goes into the pipe all at once. Okay? That data can also be placed onto the data bus of the CPU with a single fetch instruction. We've talked about fetch a couple of times because of its alignment on a 4-byte memory boundary. And here's a nice little graphic that I threw together here. So this is 9 bytes of memory. And if you notice the very first byte that has the value 01 in it, the address of that byte is 400,000. Now these are just some numbers I threw together to make it easy to look at. The number 23 is at the address 400,001, 45, 400,002, and so forth. And if you see the red lines there, they delineate the blocks. So the first block, which starts at address 400,000, ends at address 400,004. So that's our first block. The second block starts at 400,004 and goes through 400,008. That's our second block. And those are basically, are those words? No, the 4 bytes, yeah, those are 32-bit words, double words, I should say, right? So on a 32-bit system, that would be the blocks, 8, 16, 24, 32. Each byte is 8 bits. So the red lines show these boundaries of the 4-byte blocks, and each byte starting at 40,000 has its own address. And that's something to remember too. You can access data, any byte you want in any address. Every byte has an address. But we're talking about a little bit higher of a level thing here called a block. And it may or may not be implemented that way in the hardware, but that's a good way to think about it, is that you align data on these block boundaries, and you're going to be improving performance quite a bit. So here's what it might look like in the data section of your program. this memory right here that we've got, what might it look like in the actual data section? Well, you can see, and we can ignore line 7 for right now, but you can see that I aligned on line 8, I aligned the next variable on a 4-byte boundary called variable 1, and it has the values 0, 1, 2, 3, 4, 5, 6, 7 hex. Variable 2 is right underneath that with 3, 4, 5, 6, 7, 8, 9, 0. Now, how do we know that variable 2 is aligned on a 4-byte boundary? Because variable 1 is 4 bytes. So variable 1 starts at a 4-byte address. It's 4 bytes long, thus variable 2 follows right after it, and it is 4 bytes as well. So that align 4, and in an ARM processor, it would be a dot align space 4. What that align 4 does is it pads. So let's say that test 1 is on a 1-byte or 2-byte boundary. Align 4 will say, okay, we're not quite at a 4-byte boundary here, so I'm going to add a bunch of no-ops. In ARM, it adds a bunch of zeros. So I'm just going to pad the data between the end of line 7 and the beginning of line 9. I'm just going to pad that with a bunch of 90s on Intel and a bunch of zeros. And we're going to see an example of that. And a bunch of zeros on ARM. So again, after seeing that code, what are we actually looking at? The number 0, 1, 2, 3, 4, 5, 6, 7 starts at address 400,000 and ends at address 400,004. We kind of already talked about that. This number is aligned on the 4-byte boundary of 400,000. Same with 3, 4, 5, 6, 7, 8, 9, 0. It's within. So you can think of that water pipe I was talking about as being the red bars, in between the red bars. So our data fits perfectly in there. So when the CPU reads the first number, that 0, 1, 2, 3, 4, 5, 6, 7, into one of its registers, the memory chips only need to issue a single fetch to the actual memory chips. The memory chip controllers only need to issue a single fetch to the memory to put that number, 0, 1, 2, 3, 4, 5, 6, 7, onto the data bus and send it off to the CPU. Same goes for the second number, 3, 4, 5, 6, 7, 8, 9, 0. However, what if I put that letter A in my data section, and then I put my 2 double word numbers? So I have the letter A and then 0, 1, 2, 3, 4, 5, 6, 7, and then 3, 4, 5, 6, 7, 8, 9, 0. Are you noticing a shift? There's a shift to the right by 1 byte. So 0, 1, 2, 3, 4, 5, 6, 7 is no longer aligned on a 4-byte boundary. So what happens when I tell the memory chips I want that variable? I want the number 0, 1, 2, 3, 4, 5, 6, 7 sent to the CPU. What happens? Well, it fetches 0, 1, 2, 3, 4, 5. Then it has to fetch 6, 7 from the second block, put them together, and then send them on the data bus. That's a very simplistic explanation, but I think it's a pretty effective one. So because they're not aligned, you actually have that issue. And here's an example of that. Just as a reminder of our code, we've got our data, or we've got our test 1A, then we've got the align 4, and then variable 1 and variable 2. And this is what the memory actually looks like. So if you notice, our letter A is the hexadecimal letter 40, a hexadecimal value of 41. You can see it over there. It's pointed to our letter A. And this program, by the way, is called GHEX. It is a program that is free on Linux. There's also one on Windows, and it also is available on Linux ARM. But GHEX is a great little program. And so you can see our 41 and our A, and then we've got 6, 7, 4, 5, 2, 3, 0, 1, but it's backwards, right? The reason why those numbers are not 0, 1, 2, 3, 4, 5, 6, 7 is because of little endian order. But you can see each 4-byte block, and you can see the A is first, and then 0, 1, 2, 3, 4, 5, 6, 7 in little endian order, but it moves over into the second block, right? So our first number kind of expands over to the second block to the right. So the 2, 3, and the 0, 1 to the right. So it has to be grabbed in 2 fetches. And you can also see our second number, which is 3, 4, 5, 6, 7, 8, 9, 0. And again, little endian order reverses those. And I have a video on little endian order. I might put a link to that in the description of this video. That also expands to the second block. So we have a problem. Now, the code will work. It will run. It will give your mathematical, whatever you're doing with that data, it'll do it correctly. but the problem is performance. It has to do two fetches instead of one. Now here it is with the align. So this one right here was without the align. Okay, this one right here is with the align. If you remember our code, we have the letter A, align 4, and then we have our variable 1 and variable 2. And that's what we're looking at here in memory. So the number 41, which represents A, that is at the beginning of that block. And then that align 4 said, hey, pad out until you get to the next 4-byte boundary. So what it did was it put 3 90s, which if you remember, machine code 90 means no op in your text section. I don't know why they did it that way. I like the way ARM did it better. It just put zeros in there instead of 90, but that's the way they did it in Intel. And so that way, 0, 1, 2, 3, 4, 5, 6, 7 is fully encased in the next block, and so is our second number, 3, 4, 5, 6, 7, 8, 9, 0. And again, those numbers look reversed, and that's absolutely how they are in memory. It's called little endian order. You can take a look at that in another video that I have. So that align 4 padded those 3 bytes so the variable 1 and variable 2 could be placed on a 4-byte boundary. I think that's pretty cool. Now, I thought to myself, well, what if can we align on something that's not a power of 3? So notice on the code on the right here, I tried to do an align 3, and when I tried to build it, it said error, segment alignment 3 is not a power of 2. So that's evidence that you must do things with a power of 2. Now, one thing I find very interesting is ARM doesn't care. If I said align 3 on ARM, it would do it. That would totally screw up the performance of your app if that's what you're worried about. It's always good to do things based on a power of 2. Always, 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 no matter what operating system you're working with. Okay, so now that you kind of see what alignment's all about, what about higher level languages? Can we do this in higher level languages? The answer is absolutely. Since C++ 11, there's an align as parentheses function that allows you to specify how you want your variable aligned. So align as parentheses 32, maybe for a 32-bit operating system, and then you specify the variable declaration. So you would say align as 32 in parentheses int my integer, whatever the name of your variable is. Or if you want to align an entire structure, you would say struct align as parentheses 32, and then your complete structure declaration. So this forces a variable or a structure to be aligned on a specific byte boundary to enhance performance on some CPU architectures. And you can also align things based on a data type. There's an align of function where you specify in its parentheses the data type, and then you use that as an argument into the align as. Now, why would you do something like that? Well, what this will allow you to do is it'll allow you to, instead of hard coding the 32, it'll allow you to use the compiler to make that decision so you can better easily compile across operating systems. So that's actually probably the best way to do the align as. But also be aware that most modern C++ and C compilers will actually modify your code to set up the most efficient alignment for your application. So I've written code in C++ where I've put all kinds of variables in there. I didn't worry about alignment. When I looked at the machine code that was generated, it actually moved things around in the data section so things were automatically aligned. So the compiler is pretty damn smart. It will do things as much as it can to improve the performance of your compile. So in summary, there are 3 primary reasons to align memory. The CPU architecture may require it. Remember the FX save, that's a specific instruction. That's the second possibility. The third primary reason is performance can be enhanced by aligning your data. However, this creates another problem. It might not be that big of a problem, but you do get wasted memory. Remember those 90s, that padding? You've lost 3 bytes. Well, if you're dealing with a 16 gigabyte computer, maybe that's not that big of a deal. Now, looking on the internet, looking on Intel's website, looking at the ARM developer website, I wanted to make sure I got this right. is performance really an issue these days? Do you really have to worry about performance at this level? You're going to see a bunch of people arguing about it. My answer is both yes and no. It depends upon the CPU architecture. I saw a study done where it says that Intel shows that its complex instruction set computing CPUs do not substantially benefit from memory alignment when it comes to performance. However, I saw another study, NUMA processors, and I can't remember off the top of my head what NUMA stands for, but what NUMA is a processor that has multiple cores. There's a lot more to it than just that. But however, a study of NUMA processors by Intel shows a performance increase is beneficial with aligned data. ARM processors such as MIPS do benefit from memory alignment when it comes to performance, and that is primarily because of the pipelined nature of RISC processor CPU. If you don't know what pipelining is, stay tuned. I'm going to be doing a video on pipelining as well. So, what do? Go ahead and align your data. If you really are worried about performance, aligning your data can make things faster, whether people agree with you or not. It's arguable. Just align your data, okay? So when you're getting ready to publish a program and it's not compiled, it's assembled, take a look at it and say, maybe I could get a little bit more performance out of this if I align it. An Intel statement basically here is data alignment is a method to force the compiler to create data objects in memory on specific byte boundaries. This is done to increase the efficiency of data loads and stores to and from the processor. That's something I didn't mention. If you have memory also that's aligned, saving data from the CPU to memory is also increased in performance. So if you're doing a lot of memory work, like processing a graphic image, it might be a good idea to align things. And even Intel says, without going into great details, processors are designed to efficiently move data when that data can be moved to and from memory addresses that are on specific byte boundaries. And for the NUMA processors, the most recent processors out of Intel, the byte boundary is 64. So it's always a good idea to align things on 64. So since both ARM and Intel processors arguably benefit from aligned memory data, just take the safe way. Just go ahead and align things if you're worried about performance. If you're not worried about performance, if you're writing a program that uses a lot of user input where the user's typing in, maybe performance isn't that big of a deal to you because you're waiting for the user to do things, and the user's so much slower than the computer. You can also align data in assembly language by rearranging data allocations. Like for instance, if you've got if you've got a byte and then 2 double words, instead of having the double words after the byte, put the double words before the byte. That way they're automatically going to be aligned on that 64-bit or 32-bit boundary, and then the single character won't be. So by rearranging things, and it takes a little bit of arithmetic in your head and knowing how big everything is. And also in the higher level languages like C or C++, the compiler will probably rearrange your data allocations to allow for better alignment for your app. Now I do have some articles on this. I'll go ahead and put these links into the discussion or into the description of this video. I recommend that you go take a look at this if you really want to learn about how the processors work. These are really good. These are really good little articles that I found for you. So there you go. So that is data alignment. If you're getting ready to release your product and you're worried about performance, align your data. If you're not really worried about performance, it's not necessary, except if you're using specific commands, specific instructions in assembly language, and the programmer's guide will tell you all about that. Hope to see you in our next video.